that so this is the type of front that you can use, and the idea is that you build your own calculations here. This is the ones I built, but you have to build your own, and it can be similar or different, whatever, but basically it's the same concept. You can use these definitions, the same definitions if you want. That's fine. And this is you can use the same chart here. That's okay too. So you can use the front, the chart, and the definitions, but you have to build your own kind of calculation methodology. This is just to show you where these CPs were obtained, right? So they are the actual CPs rather than the average integrated CPs, so they're not so perfect. And here are some examples to show you how to do some calculations with moisture content and cyclochromium, the psychrometric chart. I have no idea why they're so. Okay, so example of calculations at two different pressures. So the two pressures there are here and in some place low pressure. So you guys can go over that. Here is how to make this these curves here. You see this saturation curve. So this one is the saturation curve. This is one at 80%. This is one at something 20-something%. So here is how to calculate them. You can go over those calculations and sorry, here example. So here they are calculated. Here is just the here is the saturation pressure. You see it's just the Antoine equation, no? So these are the temperatures, and this just use that and then multiplies by saturation, which is 1. And then here is 0.8 or 0.15 or something. So they just multiply, and then here is the same calculation that we did a moment ago, you see? Is the partial pressure divided by the atmospheric minus partial pressure multiplied by the molecular weight of water divided by molecular weight of air multiplied by 1,000. That's how it calculates the moisture content. Right? So it's a way of calculating a curve, and it's exactly these curves here that you see in color. So at every temperature, we calculate the moisture content and we plot it there. So it's that calculation there for different relative humidities. So we use the Antoine equation, take a temperature, use the Antoine equation to find the vapor pressure. So that is done here in this, and then this is the vapor pressure. Then that vapor pressure, you can multiply it by some relative humidity, 0.8 or 0.21 or whatever you want. And then, so these columns here have the partial pressure. So you can call this the partial pressure of water, partial pressure of water, partial pressure of water. And these ones are the actual moisture content at the corresponding thing. For those of you who like weird formulas in Excel, that's how you make formulas with words in Excel. So if I change this, instead of putting 80.8, I put 0.73, then you see what's happening. 73, then you can see that also the title there changes to 73%. And then what it does is here calculates then the J34 is this partial pressure. Okay? So partial pressure over atmospheric minus partial pressure here, multiplied by the ratio, then molecular weight of water over molecular weight of air, multiplied by 1,000. That's the moisture content. And these are plotted in this graph here. There's the blue curve is the saturation, the orange curve is whichever we put there, 80%, 70%, and this one is for an example that's there in those calculations here that ends up giving 21%. And here's how you determine the moisture content if you have the dry bulb and the wet bulb temperature. So here's how we do it. First, you use the Antoine equation to find the vapor pressure of water at TWB. And you use this equation here. Second, you find the moisture content and the saturation condition. So this is what we did before, right? And it's done here in this step. Third, you compute the enthalpy of the air saturation, enthalpy of the water at saturation, enthalpy of the humid air at saturation. So you see all these steps here that you can see here are the ones that we did at the beginning over there. The numbers here, by the way, I don't know if you noticed, sorry, I didn't exactly. So the numbers up there correspond to the steps down here. And then these are the calculations we are doing in this direction. Okay? So the explanation of the calculations are here. And here are the calculations that we're doing them. Here are the units. And here are the names of the things that have been done. So it tells you step by step how to calculate your moisture content when you have the experimental data, such as wet bulb temperature and dry bulb temperature. And the way to put these equations here, for example, is you simply go in there and you put the calculation. So here is you calculate your enthalpy, then the total enthalpy, then you find the enthalpy of the dry air, the enthalpy of the water, and then you calculate the moisture content, and that's where it ends in 8. And then, because I want the result to be together with this, because it's the result of this and that, then so if you change these two numbers, then that will change. If instead of 70, I want to have 65, then it changes my moisture content. Okay? So whichever data you have, you can, from the lab, for example, you can always immediately estimate. This estimates that based on assuming that the enthalpy is about the same. Now here, as you can see, it's assuming that it's using a very simple assumption, and is that the specific heats are, as I said, not the integral specific heats, but just that they follow those curves. And you can see them there. You see? You see how the specific heats use the temperatures, squared, linear. This D71 is this here, and then multiplied by temperature. So that's by HW. All these things in the bracket is the specific heat multiplied by temperature. All right. So that's one of the information you have here, and then you have another example here of calculations, but at different wet bulb temperatures. You have different enthalpies, different moisture content saturation, pressure, enthalpy of the air, enthalpy of the water. And here you have that little plot that I was telling you about, the natural logarithm of the enthalpy, the natural logarithm of the moisture content, and the wet bulb temperature. And you can find that there's three sets of information and three different correlations, and you can use any one of those sort of to get an initial idea, no? Okay. So let's go back to our simulator here. So what are the two main parameters that we controlled when we were working in the lab? Well, we had this temperature, right? We set up there a temperature at the exit of the furnace, and then the temperature in the spray dryer was about 40 degrees less than that. So right now, what we've done here in this is set that temperature approximately the same, about a bit less than that as well, 40 degrees less than that. So this temperature has been made about 40 degrees less than that. Very simple. So hopefully it simulates that. And then when we put a number there, this one gets updated and becomes that piece of information. And the air is given here with data, right, that we have, simply measured from the environment. And that produces this information. So where do we calculate that? Well, we just learned how we can calculate from the dry bulb and wet bulb temperature this. So we can go there into the simulation and build that, right? So the air here, we can see that all that was done was copy that example here. So we use this data that we got from that front panel, the dry bulb and wet bulb, and linked it to here. It's exactly the same sequence of 8 steps. Simply copy that, paste it here, and it produces a moisture content here, which is then placed in the front panel. So now we know the moisture content of the inlet. And on top of that, in this part, there is the first part here. If you look at it, this is connected to the spreadsheet. So because we have the dry bulb temperature, and we now just calculated the moisture content variable, then that point is automatically connected to the first point here of the spreadsheet. So if we change the room temperature, somebody opened the door and it became very, very dry, right? It's cold and dry now, right? Then automatically our point here is going to update itself, because now we have had this calculation that followed these steps that we look in the example here. Right? It's exactly the same. It took these steps here and it calculated its content. So now we can see the effect that it's going to have on our spray dryer, because we are having now an air that has much less moisture when it comes in. And it's going to also have less energy when it comes in. So if we wanted to look to understand, when we were doing our experiments, this was our air. What effect would it have been in our experiments if the air was cooler or higher? How would it happen? Would that have had an effect on our experiment? How big the effect would have been? Well, we could simply put back here our 20 and our 8, and then look, for example, down here. Oh, well, it's not affecting very much my flow rate here. It's affecting maybe my amount of propane that I need to use, affecting maybe the total amount of air that I use, right? But it's not really affecting the amount of water that I was able to evaporate, because the propane compensates because I put the temperature in the burner and I told it, go to 250, I don't care how much propane you need to use, just do it. And that's what my controller does. Negative water. So now, the next thing we can do is say, well, the pump now is there. This is my composition of solids, right? 18%. Maybe it could be 19 or 21. Change that. This is the temperature of the feed, which could also change. So maybe we were 32. And then here we know that the product normally will go out between this temperature here and its wet bulb temperature, and now it's below, so that temperature is not right. So that is something that one can go on to here, because here the fraction is 75% between the wet bulb temperature at the exit and the other one, and the dry bulb temperature. So now the air is going out. Where was the air? The air is going out at 91 degrees Celsius, but with a wet bulb temperature of 48 or something like that, so we need to correct that. So that one needs to be done by hand, because Excel doesn't do very well. One iteration there. Here I'm going to do 2 iterations. Okay, so now it's very close. Okay. So really the product is getting pretty warm there. We say going out at 88, and here it goes out and then cools down a little bit and it's going to the cycle.
So
yeah.
I'm not seeing cubic calc in the Excel sheet that we have.
No, it doesn't recalculate itself alone. Sorry?
No, I don't see it at all.
You have this version?
We have version 11.
Okay.
Should still work though.
No, one part, but some of these were only in 14, so.
Just the iteration. So there's an option in your Excel to recalculate it ever you enter something in.
Oh, but this part is manual totally. Yeah, and I added it. It was not in 11. So, so the product would go out, for example, at 80, and that. So we can play with that as if it was sort of a toy version of the spray dryer. It's not perfect, right? But the interesting thing would be to compare this with your results, with what you have in your experiment, and say, well, is this close or not, or is doing what it's supposed to do or not? Does it really reflect that? Does this logic that I have here correspond to that? So let's walk a little bit through the calculations and see how they work. So, as I explained before, this calculation of the moisture content of the air was done in that sequence. Now, how did we do the combustion? Well, let's take a look. We know we want to be at 250, so let's go down to a section here called combustion. And first thing is there's a section there for the enthalpies. So there is some enthalpies for the air. All these are enthalpies for the air. So maybe put them in a particular color. This is the color of the air. And let's do the color for the water. What color is water? Greenish. Greenish color of the water. That's what it says in the Congadin song. Have anyone heard the song of Congadin? It says, I used to spend my time in Angel Sonic Climb serving Her Majesty the Queen. Oh, you guys have to hear that song. Jim Cross. Does anyone know a guy named Jim Cross? No. You guys definitely are young. Yeah. So here are the temperature, the specific heat, and the enthalpy of the air going into the combustion chamber, out of the combustion chamber, and into the spray dryer. So, no, I'm confused here. No, sorry, this is the air, yeah, exactly. So the air going in from the room, then out of the combustion chamber and the spray dryer, because it cools down between the combustion chamber and the spray dryer, right? So it comes from the room at 17 degrees now, because we said 17. It burns and then it goes to 250 and then it goes down to 210. So these are there are the specific heats, and the same are the temperatures. And here are the enthalpies for the water vapor in each one of those conditions. And here are some stoichiometric factors. So these stoichiometric factors, I calculate them using the mass ratios between the different components here and oxygen. These are 5 multiplied by 32, 4 by 18, 44 by 1, 3 by 44. This is the combustion reaction using the mass, molecular mass of each one multiplied by the number of moles in the reaction. It's one way of doing stoichiometry. You guys know about stoichiometry? You ever know that? Ever knew that? It's the nanny of the chemist. They want a chemist, a little chemist, to become a grown-up. They hire stoichiometry to take care of it. So, but if you don't know stoichiometry, you cannot do chemical engineering, because all the reactions depend on stoichiometry to do all the mass balances, right? So you can do any stoichiometry that you want, but basically what you want to make sure is that you have the proper ratio between oxygen and propane, so that the amount of heat produced by the propane is enough to heat up the air to the final temperature. And so here is one way of doing it, and in the end you end up with some oxygen, nitrogen, water. Now what I did here to make my life easy is that I took the mass of dry air to be 1 kilo. 1 kilo of air has 233 grams of oxygen and 767 grams of air. So I call dibs on this one. No one else can use it. You guys have to invent your own stoichiometric tricky thing to do it. It's divided by 10. I don't know. So there's many ways of doing stoichiometry. You guys did this in chemistry and you got tired of it. So do whatever you want with your stoichiometry, just so that you can calculate the amount of air that you need. And from there we get the amount of water that we